Hello everybody, thank you for joining us for our latest Tech Talk. Today's Tech Talk is on basic design principles. I'm Steve Musa, one of the project team. I'm joined by our technical director, Jayesh.
Hello everyone.
So let's jump straight into this, Jay. Basic design principles, we're going to look at how you and the team design or bring to the project a carbon fiber solution. So
we'll start with first why we use carbon fiber. So carbon fiber is a very high strength and lightweight material, and it is becoming quite popular these days, and it's being used by contractors, project engineers, structural engineers, designers, architects, everyone. The reason is, as I said, it's very high strength. So just to give you a feel in terms of number, it is at least 3 to 4 times stronger than steel and at least 7 to 8 times lighter than steel. So you could see strength to weight ratio and why people prefer to use FRP over traditional methods. On top of that, it can be used on concrete, steel, rattan, cast iron, even on timber structures. So you can see pretty much all type of structural construction materials can be strengthened using carbon fiber. So that's why it's becoming quite popular. But the most important thing to note here is that this is a composite material. So there are at least 2 materials mixed together to make FRP, which is a very important point, especially for designers.
One of the things that we're asked quite a lot, people think this is a new technology, but it's not. That's not the case.
No, it's not entirely new. As compared to concrete and steel, you can call it as a new technology. But this was first used in 1944 in aerospace engineering. Then they started making all the aeroplanes, fiber boats, motor cars using FRP. And then in 1988, this was first used in construction.
Right.
So it's at least, like more than 30 years old technique which is used in construction. So it's not entirely new, but as compared to concrete and steel, it is still a new technology.
And because of the low profile, architects are becoming more and more aware, and they like to use it as well.
Yeah, so the typical thickness of one layer of carbon fiber is around 1 millimeter. So imagine if you're able to strengthen a beam, column or a slab with one layer of carbon fiber, or even if multiple layers, you're increasing its dimension by millimeters, which is negligible in overall scheme, and that's why architects prefer to use it, because you're not changing the shape and size of structure significantly.
And we're seeing quite a big uptake on main contractors going to designers and asking them specifically for a carbon fiber solution, purely on the basis of economy.
Yeah, so it is a very economical solution if we see the whole cost in terms of material, labor, disruption to the structure, and most importantly, time in doing that strengthening.
Yeah.
But sometimes what happens is that people only compare the cost of carbon fiber with just cost of steel and concrete.
Yeah.
And they find it expensive. But in reality, it is the overall cost which matters, not just the material cost. And if someone sees the overall cost, then this will be the most economical solution. Yeah,
I think what we found is on a lot of projects that we're able to reduce the program times on site, which obviously is something which is very beneficial.
It is, yeah. For that reason, it is being preferred by contractors as well.
So we're looking at the basic design principles and what you and the team would look at to put together a carbon fiber solution. So let's talk a bit more about that.
Yeah. So before we go into the actual design, let's see what type of strengthening commonly we do with carbon fiber. So most common elements strengthened with carbon fiber material or FRP in general are columns, slabs and beams. Slabs and beams are strengthened for flexure and shear, whereas column is strengthened for axial load or bending in combination. So these are the common type of application. We also do wall strengthening for new service or other penetrations and everything. But from a technical point of view, these are the 2 type of application we do. So slab strengthening, beam strengthening, we are relying on bond between FRP and concrete. So that's why they are called bond critical application. Whereas in a column strengthening, where we are confining a concrete element like a circular column or something, we rely on contact more than the bond. So the bond doesn't matter that much, but the contact matters. That's why you have a minimum overlap requirement as per TR 55. So these are technical applications, which are only 2. One is bond critical and another one is a contact critical application. If we go further into the carbon fiber strengthening or FRP strengthening using these kind of composite materials, so in terms of the approvals and acceptance, the minimum approval any system you propose to be used in UK has to be CE marking. That's the least approval. There are some additional approvals available, for example, ICC approval, which is International Code of Council, that is specifically for construction industry. So some of the FRP systems have got that. UL approval is for fire protection. So if anybody is proposing any sort of fire protection coating on FRP, then that needs to be UL rated.
I mean, because that's quite a key issue, really, because I think it's a bit of a people still believe that you're not able to protect carbon fibre during a fire, and it can.
Yeah, you can fire protect it. It's a misconception in the industry that carbon fiber cannot be fire protected, but that's not entirely true. Yeah, it doesn't need fire protection. That could be the case. In fact, in most strengthening schemes, you will find carbon fiber doesn't need fire protection because of the structural requirements. But in terms of building control requirement, if that is needed, then there are different types of fire protection system it can be used. Now, in terms of design, if we are designing it in the UK, then the document to follow is this Concrete Society document TR55. That's the design guideline to design FRP in the UK. TR57 gives you guidelines in terms of the application and testing, that how it should be applied, maintenance and testing kind of requirements in TR57.
Okay.
Then there is also ACI 440, which is American Concrete Institute document. That is also a design guideline available, majorly followed in America, but even people here follows ACI, even to cross-check their designs. Then we have FIB 1814, which is followed in the rest of the Europe. So these are the three main design guidelines which are used worldwide to design FRP. Now, if you note, I'm saying they are design guidelines. And that is the reason you don't see many structural engineers or designers taking up FRP design, because it is still done based on the guidelines and there is not a set code available to design FRP. But to change that, a team which finished the latest edition of TR55, which was edition 3, they were working to put an annexure in Eurocode 2, and that is Model Code 2021 that was included. Hopefully later on this year we will have a Eurocode 2 with an annexure for FRP design. So soon we are going to get a Eurocode which will give a bit more clarification in terms of designs, concepts and all those things.
Okay.
Right, if we go and look into the properties of carbon fiber or mechanical properties, the curve we are seeing on the slide is stress strain behavior of FRP, and it is compared with the steel. So we all know the black curve, which is the behavior of steel. We design it on the yield stress. So it's a very straightforward design in terms of steel.
Okay.
The top green line shows the behavior of carbon fiber. The bottom green line shows the behavior of glass fiber. These are the two most common types of FRP materials which are used in the industry. So from this curve, we could see that carbon fiber is stronger than steel and glass is better deformability or ductility, if you like.
So when would you look to use glass, let's say?
So glass fiber is generally used for structures or requirements where we are expecting a movement in the structure. For example, earthquake forces or vehicular impact on a bridge pier or something like that. That's where glass fiber is commonly used.
I see.
Because we're looking for ductility in the structure. The carbon fiber is generally used for pure strength. So if we are adding additional stories on an existing structure or building, we need to strengthen beams and columns, we will look to use carbon fiber. Because we want to use less material but get more strength out of it. So these are the common areas where you use carbon and glass. But the other thing we can see from this stress strain behavior is that both carbon fiber and glass fiber, or any FRP for that matter, has a linear elastic behavior until they fail. So you can just keep on loading the carbon fiber and it will fail at a particular load, but the ultimate failure is brittle in nature. There is no yield point in carbon fiber or glass fiber. So for that reason, FRP design is or will always be a strain limit design. So FRP is not designed based on the tensile stress given on the data sheet. It is designed based on the strain limitation. So how do we approach design is that we just get the modulus of material and the thickness of material from the data sheet. Then we limit the strain depending on the guideline we are following to design, type of strengthening we are doing, type of load we are putting onto the structure and all. That will govern a strain value. That design strain value is used and it's multiplied with the modulus from the data sheet. That will give you a design stress for that particular element, for that particular requirement. And then you calculate the area of FRP required using that designed derived tensile strength. So that's how we design FRP. So this is the major difference between steel and FRP design, because in steel we already have the yield stress, which could be 500 MPa, 400 MPa depending on grade of steel, whereas in carbon fiber we need to derive that tensile stress depending on the strain values and all those things. The other thing, which is the most important thing, as I said as very first thing in this tech talk, that carbon fiber is or FRP is a composite material. So there are at least two materials mixed together to make FRP. So especially whenever we are designing a fabric system or wrap system, as we call it commonly in the industry, that needs to be always designed on final cured laminate property.
Okay.
So we can see on this stress strain curve, the top blue line shows the behavior of fiber only. Then we have an epoxy matrix, which is the purple properties, which is much lower than the fiber properties. So when you mix them together, you'll get the property of FRP between these two somewhere. So in the final design, we should always consider these final cured laminate property and not dry fiber property.
So I think I'm right in saying in the past and earlier designs, people were using the dry fiber properties, but this is, you've got to be very careful, yeah?
Yes, yeah. So you don't design fabric system on dry fiber properties, because as soon as you mix it with the epoxy matrix, the modulus will drop, thickness will increase and all those things. So you should consider those kind of values. Here's an example of that is shown here. So these are two data sheets we could see. So in both we have typical dry fiber properties and composite gross laminate property, which is the cured laminate property. And that is another thing which designers should note, that whichever material they are using, if the data sheet doesn't provide them the final cured laminate property, they should ask the manufacturer for those properties. Because as I said, in the design, we should always consider these final cured laminate property. Now, if we see on the data sheet on the left hand side, we could see that the dry fiber modulus is around 230 GPa, but the cured laminate modulus drops down, the design value drops down to 82 GPa. So there is a huge difference between 230 GPa and 82 GPa, and the thickness remains same. So if you design based on 230 GPa, you'll end up using just third of the material which is actually needed onto the structure. So for that reason, you should always consider it or design it based on final cured laminate property.
It's a critical, important point, yeah.
It is, yeah. The other critical design aspect which we need to make sure or give consideration to is basically using of anchors or anchorage means, because whenever we do strengthening of slabs and beams on top, we come across an obstruction, or wherever we are strengthening, we might have an obstruction in the way. So practically we can only take the FRP up to that point or that end, and then we will stop it there. But in negative moment strengthening, that's the location where we have the peak stress. So if we stop or curtail the FRP at the location where we have the peak requirement or peak stress, there's no point in doing that strengthening.
I see. Yeah,
so we need to have some sort of anchorage detail there, or development length or something that could be done using carbon fiber anchors, or it could be done by wrapping the FRP up onto the column, then put additional hoop around it. But there has to be some sort of detailing there, and engineers should ask for these kind of detailing from FRP designers.
So basically what you're saying is if you're wrapping the beam and you don't go to the ends and use anchors, it's not worth doing.
Yeah, unless you have the peak stress somewhere in the span, it will not work on that location, because you don't have any anchorage length beyond that point. The other thing is in terms of shear strengthening of the beams. So if we can imagine putting like a link or a stirrup from the outside of a beam, usually people they just put a U-wrap around the beam and leave it like that. There is no closing detail there. But there is another way we could do that, is by using these anchors. We can drill a hole between the slab and beam junction, use these anchors, and then display them on already laid FRP, cover them with another layer. So by that way, you have one system which is actually going into the concrete. So it provides you a similar effect as in closed loop, rather than just like a U kind of link there.
So that's the diagram on the left, yeah?
Yes, it is, yeah.
Okay.
Then if we try and see the use of bigger anchors, it's not here. So there are specially designed anchors as well, which are called super anchors, which we use to transfer forces from one side to another side. So the image we are seeing of the anchor next to the left hand image are nominal anchors. So they are standard size 150 millimeter. But if we have a bigger column size, we can use a longer anchor, which is called super anchors, which is used for which is specially designed anchors and designed for a particular force.
Okay.
Right, we'll see column strengthening. So in terms of column strengthening, as I said, that this is a contact critical application. So the concept behind is just the confinement. So what we do is that we confine the concrete with a much stronger material from the outside. So that is the reason that circular is the best shape to strengthen, because we have even stresses throughout the perimeter of the column. So when the load comes on top of it, the column will start to dilate. FRP provides resistance to that dilation, so that's how it's strengthened. So it's a very straightforward confinement principle there. The same theory we could use for square and rectangular columns, but up to an aspect ratio of 2 only, because after that, stress concentration will be in the corners fail first, so the confinement will not be that effective.
On a sort of preparation, I know we'll talk about that later on, but the corners have to be chamfered?
Yes, so there is a minimum requirement to round off the corners to a minimum radius of 20 millimeter.
Okay.
And that's a design requirement, so we need to do that. If we have sharp corners, we may have premature FRP rupture, so for that reason corners need to be rounded off.
Okay.
But similarly, if we have higher aspect ratio columns, then we should technically look for the combined axial and bending analysis, especially even up to aspect ratio 2 only. So like this slide shows an NM interaction diagram for a column. So what happens is that when you confine the concrete becomes stronger, so your interaction diagram or this curve will shift outwards, so your moment and axial force would fall into the curve. So that is an indirect way to strengthen column for both combined and axial, combined bending and axial effect. So that's how we can strengthen it. But again, we have to draw these kind of NM interaction diagram for different strengths of concrete and see which one is suitable. Then that confined concrete strength requirement should be given to FRP designer, that we have a column which is currently X MPa strength, but we want to go up to Y for the new moment and axial load to come into the curve. Now, if we have even bigger aspect ratio columns, like wall kind of column or blade column as we technically call them, in that as well we can use the same principle of combined bending and axial, confine them, and then see whether just the confinement is effective or not. But if it is not, then what we could do is that we could use the super anchors or carbon fiber anchors going through the longer edge of the column. So in this slide we could see the left image on the top shows the column without these anchors. Now what it is showing is that your stress concentration is in the corners where it shows a reaction there, R. So it pushed that outwards, which means your confinement in the longer side of it will not be that effective. Now to change that behavior, we could use carbon fiber anchors as ties. So we can drill the anchors through, use those anchors. So as soon as your corners try to push out and your confinement tries to separate from column, these anchors will become active, and they provide additional force there or resistance there. So that's how the confinement could become effective. So that is another way to strengthen blade kind of columns.
Okay. There's something we were talking about before we touched on was the fire protection of the assets. I mean, it's something in the industry, people believe that you can't fire protect a column or a beam if it has had carbon fiber. So this is not true.
No, it's not. You can fire protect it if needed, but the most important thing as a designer you should check is that whenever you are proposing carbon fiber strengthening on any structural element, you should also assess that element in fire limit state loading. Your fire limit state loading are much less than your ULS load for which you are designing FRP. So there will be chances, or I would say more than 95% cases, you will find that your structure on its own is strong enough to carry the fire limit state load, which means your FRP doesn't need any special fire protection system structurally. Because even if you lose FRP in an event of fire, you're not going to lose the structure. So that's the key consideration.
Yeah, so that check's done at the start of the design when you look at it. So if it's found that you may need some form of fire protection, what are we offering the client? Yeah,
so I mean, even if you don't need fire protection structurally onto the FRP, there will still be building control requirements to fire protect everything for certain time limits, for example 60 minutes, 90 minutes, depending on the project. So in those instances, the different types of fire protection systems we have is like a board style fire protection system, which is like specially manufactured fire boards. So they can provide fire protection to FRP. There is an intumescent paint coating which is also tested with the FRP and got approval from UL. There is a cementitious fire protection system, which is a spray-on application. So it provides up to 4 hours fire rating if needed. So these are the three types of systems currently available in the industry which can be used if a fire protection requirement is there, or even to justify the building control requirement.
If it's required, yeah. Okay. So when you're looking at or speaking with clients, and obviously just to help them provide information, this is something that you would ask, you would send out?
Yeah, so we do provide a no obligation design support. So what we do in that, or ask the engineers in that, is that if they think of using carbon fiber or just want to explore this option, that whether it is suitable for that requirement or not, we ask for this information to do a feasibility analysis. So what we ask is that what element you're looking to strengthen, whether it's a beam, column, or a slab. Then it's section property, like it's size, shape, reinforcement detail, grade of steel, grade of concrete, and all that information the project engineer will have if they are assessing their structure. Even if they don't have the exact information, they'll be making some assumptions. So we need the same assumption so that our analysis comes in line with their analysis. So once we get that information along with the loads, like existing moments, shear forces, or axial load with proposed loads as well. So once we get that, we do an initial assessment, which we call feasibility study. And after that, we tell them whether it is feasible to use FRP or not. If it is feasible, then how much FRP is needed, how long will it take to do that work, and how much it is going to cost them.
Right.
Everything will be put into a report, which we call feasibility study report, which they can take to their client, show them this alternative way to strengthen structure. If everybody is happy with the cost given in that report, then that will come into effect. Otherwise, until that point of time, we don't charge anything. So it's a no obligation design support for clients. And that is the reason we seriously recommend to use this service, because it will give them their own experience of working with FRP. And all it will cost probably is just a phone call or an email to them.
And we respond them within 24, 48 hours, I would expect, yeah?
Yeah, the initial answer on feasibility we can give within a couple of days.
Well, thanks very much for joining us for today's Tech Talk. There's quite a lot of information, specifically on the design side. If you do need more information, if you go to our website, there's a lot of videos, a lot more content, a lot more information, or just scan the codes that you can see on the screen now, and that will put you straight through to our design team. Well, thanks for joining us today, and hopefully we'll be working with you soon.
Thank you.